in this lecture 4, I will discuss the corrections factors, those are recommended by the ASTM, and then I will go for the next test, which is the cone penetration test. So, first, as in the last class I have discussed, the as per IS code there are two corrections. One is corrections due to overburden pressure, another is a correction dull latency correction. But as per ASTM or American Society for Testing and Materials, they are recommending 5 corrections. One is the corrections due to overburden pressure, then your hammer efficiency correction, then the drill rod correction, sampler correction, and borehole corrections. So, the hammer this is the corrections due to effective overburden pressure we can get with this expression. So, where P 0 bar is the effective overburden pressure and which is in kPa. So, now next one is the hammer efficiency correction. So, as I mentioned that our theoretical input energy is weight of the hammer into the height of free fall, but our hammer efficiency is not same for different hammer. So, that is why our actual hammer energy that we are applying in the field is different. So, that is why we will get an ratio, that is the some energy ratio ER. So, this is the actual hammer energy by the input energy, and the correction factor is that ER divided by ERB. Now, ERB is the energy by which we are converting all the hammers to a standard energy. So, this is the energy by which we can represent into the soil. So, that is why in this figure it is 70. This 70 means this 70 is the ERB. So, that means the all the hammers N value we have to convert to a 70% energy. So, that means ERB is the 70. So, here, so we can see this is ERB is the hammer efficiency. So, this is the hammer efficiency correction. So, standard energy. So, that is why standard energy ratio. So, all the standard energy ratio we will convert our N value. So, that is why the if for different hammer this ER value is different. So, this is for different hammer as I mentioned in the last class, this is the different values, and we will take the if the ER value is 80, if you use the automatic hammer, then the standard energy ratio is ERB 70, that means we have to convert it, we are this is ER is 80, but we will represent them in 70. So, basically we are applied more energy, now we are representing in a lower energy. So, our N value should be increased. So, that is why it is the 80 by 70. Now, if our applied energy is less and we want to represent it in a higher energy ratio, then our N value will reduce. So, but here our standard energy representing energy is 70, which is less than the applied. So, the N value will increase. So, this is 80 by 70 1.14. Similarly, some correction factors for rod lengths are given. So, these are the tables we can use this table for different rod length, what would be the correction factor. This is the rod length and this is the correction factor. So, this table can be used for the rod length correction. Then this table can be used for the sampler corrections, whether different sampler tube, because we are using different sampler tube, and if the sampler tube is different and depending upon that our N value will also influence. So, that is why it is without liner, if there is a liner, and if there is not liner. So, there will be different correction factor. If without liner the correction factor is 1, and with liner dense sand is 0.8, loose sand is 0.9. So, similarly, for the boreholes diameter, depending upon the borehole diameters we have to apply the corrections. So, borehole diameters, if it is 60 to 120 millimeter, this is the correction factor is 1, otherwise 150 is 1.05, 200 is 1.15. So, now there is a example problem. So, if the your measured value is 21, rod length is 13 meter, borehole diameter 100 millimeter and P 0 bar is 200 kPa, ER is 80, loose sand without liner, what are the standard N dash in 70% standard energy ratio and the corrected N value in 60 standard energy ratio. Now, the your solution that ERB is, this is the standard is given first case ERB is 70. So, this will be N dash 70 because our standard energy ratio is 70. So, these are the expression. So, Cn I will get from, because your 200 P 0 bar is already given in 200 kPa. So, we can put directly here, it is kPa. Remember that P 0 is always kPa if we put it in this expression. So, it is 0.69. So, our correction factor for the overburden pressure is 0.69. Then correction factor for the, because E correction factor for hammer efficiency is ER divided by ERB. Here ERB is 70 and ER is given 80. So, this is 1.14 and it is given your rod length is 13. So, it is in between greater than 10. So, it is 1. So, it is rod length correction is 1. Then it is your loose sand without liner. So, it is without liner, again the correction factor is 1. So, it is without liner, correction factor is 1. Similarly, it is borehole diameter is 100 millimeter. So, it is in between 60 to 120 millimeter. So, it is again 1. So, it is again 1. So, finally, the N dash 70 will be 17. Initially, it was 21, now it is become 17. Now, if I want to convert these things for N dash 60, then we can write this expression. This is ER 1 into N 1 plus ER 2 into N 2. So, your N dash 60 will be 70 divided by 60 into 17. So, because this is the standard energy ratio 1 into the N 1. So, N 1 is here your for the standard energy ratio 70, N 1 is 17, for standard ratio 60, what will be the N 1. So, that is the case. So, that it will further, it will increase, because now we are reducing this energy ratio. So, it is ultimately 20. So, this is the one particular example in terms of the corrections required for ASTM. Now, I will show you the one example which I am using in terms of the IS code. So, in terms of IS code, the problem is given that we have soil layer which is saturated. So, water table is at the ground level and the gamma saturated, gamma sat is 19 kilonewton meter cube, and we have to determine the N value, which is this depth is 7.5 meter from the ground level. So, our N measured is equal to 50 and the soil type, it is a fine sand. So, soil type is a fine sand, measured N value is 50. Now, we have to apply the corrections and we have to determine what will be the corrected N value. So, first correction is for the N dash overburden pressure, which is C n and N, or N measured. Here this is the n. So, now C n we need to know the as per IS code we use this chart that I have shown you in previous class. So, you use that chart, and in this chart it is given ton per meter square. So, but the P 0 bar or P 0 dash here is it is fully saturated. So, here it will be 7.5 into, as I mentioned, this will be the gamma sat minus gamma w, unit weight of water. 7.5 is the height. So, 7.5 minus 19 minus 10, the unit weight of water we are assuming 10. You can consider 9.81 also, but most of the cases in this course I will consider it is 10. So, this will be 7.5 into 9. So, this value is 67.5 kilonewton per meter square, because this is 19 kilonewton per meter cube. So, this is 10 kilonewton per meter cube, this is kilonewton per meter square. So, in terms of ton, so this will be 6.75 ton per meter square. Now, if you look at the chart, so corresponding C n value corresponding 6.75 ton, because as I mentioned, if it is 10, then your C n, if it is 10 ton per meter square, your C n value is exactly 1. But if it is less than 10 tons per meter square, so your C n value is greater than 1. If it is less than, if it is greater than the 10 ton per meter square, your C n value is less than 1. So, here definitely C n value will be greater than 1. So, from the chart the C n value is coming out to be 1.1. So, this is from the chart. So, we will get the n dash value is equal to 1.1 into 50. So, it will be 55, which is greater than 15, and it is saturated as well as it is fine sand. It is fine sand and it is saturated also. Or fully saturated. So, we have to apply the dilatancy correction. It is greater than 15. So, the dilatancy correction, you know, this is n double dash, which is equal to 15 plus half into n dash minus 15. So, this is 15 plus half, n dash is 55 minus 15. So, this is coming out to be 35. So, my final corrected value after applying both overburden correction and dilatancy correction, the n dash value is, n double dash value is 35, whereas measured value was 50. Now, this problem will be slightly different if the water table is not at the ground level. Suppose this is just if the water table is, suppose this is it is say 2 meter below the ground level. So, if this water table location is here and this gamma bulk is say 19 kilonewton meter, or gamma bulk is slightly less, say 17 kilonewton per meter, and gamma sat is 19 kilonewton per meter. So, in that case your P 0 bar value will change. So, P 0 bar value will be in that case 17 into 2 plus 5.5 into 19 minus 10. So, this is the only difference. After that, so based on that you calculate the P 0 bar, and then from the chart you calculate corresponding C n. If it is greater than 15, you apply the latency correction. So, that is why the position of water table, and based on that. So, here the total soil is fully saturated. First case we have considered the two cases. The first case, the total soil is fully saturated. So, and saturated unit weight is 19 kilonewton per meter cube. So, we calculate this value. So, this is coming out to be 67.5 kilonewton per meter square. Now, if the total 7.5 meter is fully saturated. Now, if the water table is 2 meter below the ground level, then first 2 meter is not fully saturated, whereas the unit weight is, or bulk unit weight is 17 kilonewton per meter cube, and the saturated unit weight as it is 19 kilonewton per meter cube. So, in that case P 0 bar will be 17 into 2 plus this is the 5.5, because total is 7.5. So, 5.5 into 19 minus 10. So, you calculate this P 0 bar and then do these things again. So, as it is. So, this is the two example problems that we are doing for two cases. First one is for as per ASTM and the second one is as per IS code. So, as I mentioned that here based on the calculated n value or the corrected n value, we have some correlations. So, based on that we can determine what type of soil it is. So, for example, there is table is given if n value is for the clay, if n value is 0 to 2, and then the Cu value is 12.5, and that means Cu value is 12.5 means your undrained shear strength is 2 Cu, that is Cu is Qu by 2. These things I have already mentioned. So, this is we can. So, the consistency is very soft if your cohesion value is 0 to 12.5 kPa, the soil is termed as very soft. If it is 12.5 to 25, it is soft. 25 to 50 medium, 50 to 100 kPa steep, 100 to 200 kPa very steep, then greater than 200 kPa it is hard, and these are the visual identification, you can get this information. So, these are the correlation in corresponding Cu and the type of soil. Similarly, we have this is the corrected here. These both case these are correlation are not corrected for overburden. Remember that here overburden correction is not applied. So, as I mentioned, these correlations are given for different conditions. Sometimes it is with the only measured value, with the corrected values applying all the corrections, with the corrected value applying some correction, not applying other corrections. So, this is so you have to be careful which correlation you are using. So, and these conditions you have to satisfy. So, this is the correlation not corrected for overburden. Similarly, for the sandy soil, this is the n value corresponding relative density and the type of soil, because this is the consistency, because in the consistency in the sandy soil or the granular soil we represent it in terms of relative density, and for the clay soil in terms of the cohesion or the undrained cohesion. So, this is the n value corresponding the relative density and the type of soil. So, this is the 0 to 15 is for the very loose, and 85 to 100 is very dense, or greater than 85 is very dense. So, and this is the corresponding n dash 60. 60 as I mentioned, 60 is the that standard energy ratio. And then once we get these, so there are other correlations available. So, I am not representing all the correlations for, so any here I am not giving you. If you have any standard textbook or the book reference that I have given, in those books you will get other correlations also. So, you can use those correlations. So, I am giving one or two correlations or one or two standard table that we are generally using. So, next one is that once we conduct this SPT test. So, this is the final borehole logs. So, these borehole logs, this side the description of soil, this is the RL or the depth. where we are conducting the SPT, and this is the legend. We are for different soil type, we are showing them in different way, and this is the depth, this is the RL, this is the depth, and this is sample. The sample here it is mentioned R and U. R mean the representative soil, U in the undisturbed soil. So, that means here you can see it is the clay soil, this portion is clay, where we can collect the undisturbed soil sample, but these are all sand where the collection of undisturbed soil sample is very difficult. So, that is why we are collecting the disturbed sample or the representative sample, and then so in the sandy soil we are getting the n value, because as we are not able to collect the undisturbed soil sample. If you collect the undisturbed soil sample, then we can use them to determine the strength properties of the soil. So, we are get the QU value. QU means the unconfined compressive strength of the soil. So, CU you will get CUU is equal to QU by 2. So, here as it is the undisturbed soil sample, we can use determine the C value, but here it is not the undisturbed soil sample, it is the disturbed soil sample. So, here we will get the n value. So, finally, this is the 6, 18, 20, 50, 62, 50. So, these are the n value. So, and here the refusal is given at 30 meter depth, and what are the condition for refusal I have already mentioned. So, here this is the measured n value. Now, after that you have to apply the corrections and you will get the corrected n value. So, this is the end of our standard penetration test part. Now, these are the references. So, that we are these are the common references I am using for all the classes. So, next one that I will go is for the is our the penetration test, that is so next one is the penetration test, which is another indirect method. So, we have go for the standard penetration test, previous class and this class. Now, we will go for the cone penetration test. So, this is also another indirect method. So, the cone penetration test, it is two types. One is the dynamic cone penetration test or DCPT, another is the static cone penetration test or SCPT. So, the difference between these two is the dynamic cone penetration test is similar to the SPT. That means, we have to apply the hammer blow to drive the cone, and what static cone penetration test, we are not applied any hammer blow. So, we are pushing it into the soil with a particular rate. So, here 1 centimeter per second. So, with a 1 centimeter per second rate, we are pushing this cone into the soil. So, and the another difference, we are continuously measuring the data. So, you will get the continuous measurement in case of SCPT. So, the first I will discuss about the SCPT, then I will go for the DCPT. So, the this is the some description that you, so this is as per 4968 IS code part 3 1976. So, this is the static cone. This equipment consists of a cone, friction jacket, sounding rod, mental tube and a driving mechanism and measuring equipment. So, this is the SCPT. The cone have a apex angle is 60 degree plus minus 15 second, and overall base diameter is 35.7 millimeter, and the cross section area of the cone is 10 centimeters square. So, there is a friction sleeve with an area of 150 centimeter square, and this is the sounding rod 15 millimeter diameter, which can be extended with the addition rod of 1 meter for each length. So, which is common for any test, whether it is SPT or DCPT or SCPT. So, that means you can add the rod and you can increase the required depth of the test. So, that means you can increase the rod length. by adding one after another, and you can conduct the test for up to the required depth. So, here the driving mechanisms would have a capacity of 20 to 30 kilonewton, and it is for manually operated equipment and 100 kilonewton for mechanically operated equipment. So, these are some informations. So, here this is the procedure which is explained here, but you can read this procedures that how it is been explained, but I will show you with the help of animation. So, that will be, I think that will help you to understand these things in better way, how these equipments actually works. So, there are basically the 4 steps or 4 position by which we can conduct this test. So, first position is that, so as I mentioned, there is the 4 components. One is the sounding rod, one is the mental tube, friction jacket assembly and cone assembly. This is the sounding rod, this is the yellow one is the mental tube, this black one is the friction jacket assembly, and this one is the cone assembly. So, this is the overall picture of the cone. So, now this is the first stage. So, what we will do, I will push this total sounding rod along with cone assembly is pushed by 40 millimeters. So, this is 40 millimeters, it is not visible here. So, I can write for you. So, this is 40 millimeter. So, this is 40 millimeter. So, first stage sounding rod along with the cone assembly is pushed by 40 millimeter. So, we will get a resistance which is given by the soil. So, that resistance is measured. So, that will give you the cone resistance. So, it is the advantage of the static cone penetration test is that here the cone resistance and the frictional resistance we can calculate separately. So, that will be helpful for our pile load carrying capacity design, because we know that pile it has the cone resistance and it has the frictional resistance. So, here first stage when the sounding rod along with the cone assembly is pushed into the ground by 40 millimeter, we measure the resistance, that will give you the cone resistance which is the QC. So, you will get the QC which is the cone resistance. In the next stage, this is the same stage. In the next stage, your sounding rod, cone assembly and the friction jacket, all 3 are pushed into the ground with further 40 millimeter. So, here the friction jacket and cone resistance both are pushed into the ground. The resistance that I will get, it is the total resistance. So, I will get for initial stage I will get the cone resistance, next I will get the total resistance. So, if I subtract the cone resistance from the total resistance, so I will get the frictional resistance. So, and in the third stage what I will do, what it is done, that this is the second stage. Now, third stage the mental tube is pushed by 40 millimeter, and in the fourth stage, final stage, your mental tube and the friction jacket both are pushed by 40 millimeter. So, total 80 millimeter penetration is there, 40 plus 40, and this fourth stage is the original stage when we started the test. So, these are the 4 stages. First stage we penetrate the sounding rod and the cone assembly, we will get the cone resistance. In the second stage we will push the sounding rod, friction jacket and cone assembly. So, we will get the total resistance. So, if I subtract the cone resistance from the total resistance, I will get the friction resistance, and in the third stage the mental tube is pushed by 40 millimeter, and fourth stage mental tube and the friction jacket assembly is pushed by 40 millimeter. So, total 80 millimeter penetration, we will get the friction resistance as well as the cone resistance separately. So, here I will finish this class, and in the next class I will discuss that what are the correlations, how I will correlate these static cone penetration values with the soil parameters, and then I will discuss the dynamic cone penetration test also. Thank you.